everyone, and welcome to Properties of Logarithms. If you need to brush up on your logs, this is the video for you. First of all, before I begin, I always tell students when I am teaching this for the first time that when you see a logarithm, you need to think exponents. All of our properties of logs stem from some type of exponent rule. So, when I want to talk about the common logarithm, that means you would see the common log printed as log A. Normally when we look at some type of logarithm, we see the expression log. You have a base. Then I call this a value. And if there is anything I can instill in you, a log is an exponent. A log is an exponent. A log is an exponent. So if I see log A, I don't see a number written at the base. You always assume it to be 10. So if I have log 17, that would mean log base 10 of 17, but you probably will not see it written that way anywhere among mathematicians. You'll just see it as log 17. I can put an expression behind it. If I have log of x squared plus 2, that implies that it's log base 10 of x squared plus 2, even though you wouldn't see it printed that way. Along those same lines, when I talk about the natural log, if I see the symbol ln instead of the word log, you are to assume that we have a base e. So again, some examples. If I give you the natural log of 17 or the natural log of x squared plus 2, what it means is that you would have a base e. We would never really write it as log base e of 17, but they are equivalent. You wouldn't see it written as log base e of x squared plus 2, but they are equivalent. So again, you probably wouldn't see it written that way, but that is what those mean. All right, next let's talk about the logarithm of 1. When I talk about the logarithm of 1, what we're stating is if we look at the structure, we see log, we see a base, any base of a, but if you notice the arguments or the value is 1. Whenever this value is 1, your answer is always 0. Why? Because if you exponentiate, meaning I put this in exponential form instead of logarithmic form, you always do base to the power equals the value. So in this example, we have a, which is my base. 0, remember a log is an exponent. A log is an exponent. So that means my exponent is 0. It's equal to 1. And since the exponent is 0, anything to the 0 power is 1. So some examples. If I have log base 17 of 1, well, if I exponentiate that, I'm asking myself, if I'm in base 17, what power gives me the value of 1? That's always 0. If I do log base 32 of 1. Regardless of the base, if I have a 1 in that position, I will always have a 0 exponent. Logarithm of self. So if I want to talk about the logarithm of self, look at the structure. The structure is log of any base where that base is repeated. That is always 1. Why? Well, let's exponentiate it. This is my base a. This is my power of 1. Well, a to the first is a. So if I give you log base 17 of 17, what does that mean? It means 17 to what power gives me 17? Well, then that has to be 1. If I do log of 32 of 32, what this is asking is if 32 is my base system, what is the power that gives me a value of 32? Again, that's 1. So that is the logarithm of self. I'm going to come back to inverses at the end because this is what you need in order for us whoa, what happened there? Hello, back to properties logs. With inverses, these inverses is what we need in order to get our derivative rules for e to the x and 2 to the x. So that's where those are going to come from. I'm going to do those last. All right, one-to-one equivalency. This was a method in which you use to solve equations. Basically, if I have some type of equation I need to solve where I'm in the same base, so that's important. I have to have the same base of both. Ultimately, the value that comes behind the logs have to be equivalent. So this, you guys, is a really, really simple example. But if I give you the log of x plus 2 equals the log of 3x minus 1, well, we're in base 10 because I have not written anything in the bases. And with the one-to-one property allows us, you are not mathematically doing anything with the log. You are not exponentiating. You're just saying that if I have the log of something equals the log of something, the somethings have to be equivalent. So you are not dropping the logs, but in order to find the value of x that works, all right, I would have that x is equal to 3. So that's how you would use the one-to-one property when solving a log. All right, the next three, you should remember all of these from the problems where you had to do the condensing or you had to do the expansion. And they stem from properties of exponents. So when I talk about the logarithm of a product, all right, don't we know that if we have x squared times x to the third, don't I write the base once and I add the exponents? That is where this property stems from. Log base a of u of v, I'm in base a, and this is a product. So remember, a log is an exponent. So the exponent that goes with u and the exponent that goes with v get added together. So what does that look like? Well, if I have the log, I'm going to stay in common logs just because it's easier to write. If I have the log of 4v, then I can expand that to be the log of 4. I can give the v its own log, and I would add them because this is a product. Similarly, you might have had problems where you had to condense. So if I gave you the log of, let's say, x squared plus the log of 14, you could condense that by writing it as one log of 14x squared. All right, logarithm of a quotient stems from, if I have x to the third over x squared, I write the base once and I subtract the exponents via property of exponents. So that's what we're saying here. If you are taking the log of any base and you have a value that is being divided, it's a quotient, you can give the numerator its own log and the denominator its own log. And remember, a log is an exponent. A log is an exponent. So what do you do with those exponents? You subtract them. So for instance, if I have the log of, say, 4 over v, I can give the numerator its own log. Again, I'm only doing common log because it's easier to write. Log of v, and I can subtract them because that was a quotient. Likewise, if I had the log of x squared minus the log of 14, I could go in reverse order, writing the log once, and then taking a quotient of the values. And then the logarithm of the power stems from the property of exponents, where we do x squared to the third power. When they're stacked or it's a power to a power, you multiply the powers. So if I have log base a of u to the c, you know how I keep saying a logarithm is a power? Well, this piece right here is a power, and it's being raised to the power of c. So ultimately what we can do, a lot of people just memorize, well, I just bring the c in front, but that's because now you're taking c, which is a power, and you're multiplying by the log, which is a power. So you're multiplying the powers. So oftentimes we see problems that might look like this. The log of v squared. Well, this allows me, the log of v is an exponent. The 2 is an exponent. I can write it as 2 log v. Conversely, if I have something like 4 log of 17, I can rewrite that as log of 17 to the fourth, so I can go backwards. And then the last property of logarithms I want to talk about before we start talking about inverses is the change of base. And you do need, there's a typo on here. That A should be a V. Change of base is a little bit archaic. It's a little bit archaic because right now, most of you own a TI Inspire, and you all have a log button that gives you an input value and you can do the log of any base. But let's say you don't have that log key. You have a scientific calculator. If you have a scientific calculator, that's what change of base. And I feel like change of base comes up in a future problem. I'm sorry that I couldn't put the nail on the head, but I will have to say that this is still helpful information to know. So let's say that I'm just going to go ahead and give an example. Let's say that I have the log base 4 of 17. And if you have a scientific calculator, you can't type that in. So what could you type in? Well, most scientific calculators do either have a common log key or they have a ln key. So what I can do is notice how if I look at this, isn't 4 like on the bottom and 17's on the top? I can change the base from 4 to be the common log of 10. And if you type in the log of 17 over the log of 4, you would get an equivalent expression. If I get log, or I could also do the ln. The ln of 17 over the ln of 4 gives me an equivalent expression. All right, so to show you that change of base works, I pulled up Desmos and we have log base 4 of 17. So obviously we have technology that can deal with base 4. But let's say I didn't. If I wanted to deal with another way to change it out of base 4, if I just take the natural log of 17 and I divide that by the log of 4, notice how I get an equivalent expression or an equivalent answer, but I was in base 10, not base 4. You can also use the natural log. So if I did the natural log of 17, so the number that is your value, and you divide it by the natural log of your base, those are all ratios that are equivalent. So that is where the change of base comes from. If I have the log of 17 over the log of 4, it's equivalent to the natural log of 17 over the natural log of 4. All three of these statements are equivalent. All right, let's talk about this inverse. I want you to understand these two statements because this is what is needed when we discuss the derivatives of e to the x and derivatives of other bases. So again, we need to talk about the inverse properties of a logarithm because when we want to differentiate, I don't know why that is skipping. That's driving me crazy. That's not an erase. All right, when I want to talk about the derivative, not so much of e to the x, but a to the x, we are going to need the inverse properties of logs for that proof. All right, so here we go. Okay, here's what I want you to think about. We know that inverse functions, that when I take their compositions, it equals x. So let me do a non-logarithm example. Let's say that I give you that f of x is equal to 2x plus 1. We can find the inverse by taking f of x equal to y, switching the x and the y, and we can solve for y. So this means that my inverse is x minus 1 over 2. But recall that if, I know Troy had you do this, that if you are being asked to verify that they are inverses, what is happening is their graph should reflect over the line y equals x. So if I take their compositions, if I take f of g of x, so if I take, you know what, hold up. Let me write this as f inverse of x. All right, if I take f inverse of x, if I take x minus 1 over 2, and I substitute it into f, Notice that I get x, which is the identity function. That is the part of inverses. When you apply two inverses together, they give you an identity. Remember, like 3 plus a negative 3 gives you 0. That's the additive identity. Or 3 times 1/3 gives you 1. That's the multiplicative identity. So if I go the other direction, all right, if I go the other direction, I get f inverse of f of x. So if I take 2x plus 1 and I plug it into the inverse, I also get the identity. If I graph them, we can pull up good old Desmos. All right, if I graph it, if I graph 2x plus 1, and then if I graph, what did we have? X minus 1 over 2. Notice how those two functions, all right, they reflect over the line y equals x. All right, so I hope you enjoyed that little review of inverses in general. All right, so we're going to talk about inverses as they relate to these exponentials. All right, here we go. Let's say that I give you that f of x is equal to the exponential a to the x. Remember, for a to be an exponential, I don't know why that just did that. There we go. Remember that a has to be a base that is either between 0 and 1 or greater than 1. I can't have an exponential with a base of 0. It's a constant. I can't have a base of 1. It's a constant. And I can't have a negative base because then if you graph it, it's going to oscillate. So by definition, we have stated that logarithms are the inverses of an exponential. So we know that the inverse is going to be log base a of x. Therefore, if we verify the inverses, all right, if I do f inverse of f of x, this is the one that kids get. If I take f of x, which is a to the x, and now I plug that in for x, this yields the log base a of a to the x. Well, if I exponentiate this, it is very easy to determine that this indeed equals x because this statement is asking a to what power gives me a to the x. Well, doesn't that power have to be x? So that verifies. The one that is a much harder sell is if I ask you to find f inverse of x. Because I can't do this exponentiation piece. What I have is, if I take log base a of x, and now I plug it in for that x, it yields a log base a of x, and by definition of inverses, this also has to equal x. So that is what these two things are saying. Log base a of a to the x is x, and log base a to the log base a of x equals x. So if I have log base 3 of 3 to the x, that's x. And if I have, and this is what I think is the harder sell, if I have 3 to the log base 3 of x, that is also x. And it is going to be this math fact. This right here is going to be the math fact that you are going to need when we prove the derivative of a to the x. So please keep that in mind. And if you are somebody that needs help with your logarithms, your recommended problems for reviewing logarithms is page 366, 1 to 29 odd. Enjoy.